Welcome back to our series on Applied Regression Analysis. I'm Mark Ledbetter. This is lecture video 48. We are in chapter 16. This is part 2 of how to select the best model. So in the last video, we looked at an overview of what we were going to cover in the chapter. Then we talked about the 5 steps in selecting the best model. And then we started talking about the individual steps. So we talked about specifying the maximum model with the maximum number of predictors possible or desired, and then trying to select or specify the criteria for choosing that best model. And we went over quite a few different methods or criteria, and those included the F statistic, the R squared statistic, the adjusted R squared statistic, Mallow's C statistic, and let's see, and then the press statistic, and maybe one or two others. Okay, so then we looked at the strategy for selecting variables, and we went over the different types, and then we actually looked at the recommendation to do all possible regressions. Again, this can be a very daunting task, and the constraint of each time that you could run all these models, you may have to do it in piecewise. You may have to do it in pieces because your computer may not handle that many regressions at once, okay? And so you may have like over 1,000 or even 1,000,000 different regressions. Well, when you get that high, it's just not practical to spend that much time looking at every possible regression there, okay? But if you do this method, you are guaranteed to be able to select the best model based on your criteria, okay? So in this video, we're going to look at backwards elimination, forwards elimination, and stepwise elimination, depending on how far we can get. So let's get started. So we have this example of data. So this is an example where we're going to look at all possible regressions, okay? So the maximum model for our example was, remember, this was predicting the weight of these undernourished children based on their height, age, and age squared. Okay, so the textbook is going to use these 4 criteria, so we will as well. R squared, F, MSP, and CP. Okay, so the first thing that we have are the single variables. So height, which is x1, age, x2, and age squared is x3. All right. And you'll see that the number of variables in the model is listed here. And so we have 1 for the singles, and then for higher than, so for the possible combinations of 2 variables, we have height and age squared, and age squared. Okay. They've given us the coefficients, which we're not really going to look at, but they do give us the partial F statistics, and this is either for the one model, it's pretty easy. It's just the one variable. For the one variable model, it's easy. It's just the one variable compared to the null model, right? And so that's pretty easy to look at. So you could think of that as variables added first or variables added last, but more likely you'd think about it as variables added first. Then we're looking at 2 at a time. So here we're looking at the variables. So if we look at, these are going to be variables added last, by the way, in the way this is done. So this is adding x1 last, and this is adding x2 last into the model with both. Now, the asterisks tell you how significant it is. 2 asterisks is a p-value less than 0.01. And a single asterisk is a p-value that's just less than 0.05. Okay, and so we have these models. So let's take a look. We also have the overall F statistic, the R squared, MSE, and the CP. So let's take a look first at these the single values. So for x1, let's look at the F statistics here for the one variable case. And we would want to choose the largest F statistic because that would be the most significant. Okay? And so that gives us the first one has the highest overall F statistic. Then for the R squared, of course, we want the highest. And again, that turns out to be the first one. And we're looking for the smaller MSE, and again, that turns out to be the first one. And then we're looking for a small value of CP, but close to, but not too far away from P plus 1. Okay? And so here, P plus 1 here is, I should be careful, this was for a specific example, not too far from P plus 1. So here P is 1, so P plus 1 is 2 for all of these. So the one that's smallest and closest to P plus 1 is this one. Okay? So the best single predictor is height. Okay? And we've seen that before. The p-value is usually smaller for it as well. Now when we look, so age, and you can see that age and age squared are very close to each other in this value. They're also close with the R squared, and they're pretty close with MSE, and then they're also fairly close with this mallow C. Okay? So those are fairly close to each other. Now let's look at two variables, so height and age, and we look at the overall F statistic for the two variables, which is here. Okay, so there's 3 of those. We see that the model number 4 here for height and age, it has a 15.95. It's the highest of the 3. The R squared value is the highest of the 3 is the 0.78, but it's very, very close to this one. And you notice that the F statistic is also close to the fifth model, which is the one below it. And then same thing, the MSE is not very different between the 4th and 5th model, and the mallow C, even though 2.01 is the smallest and it's not too far from 3, you might actually think that, well, it is smaller, but it is further from 3 than 2.14. We would still choose the 2.01 because the criteria is choose the smaller one that's not too far away, and there's not much difference between these two. So the best two variable model is going to be height and age, but it's very close. You could choose either height and age or height and age squared. But usually when we have a power in the model, we like to have the lower, no, I'm sorry, I'm thinking of interaction. Okay, so please forget that. We would have age in the model or age squared. Either one would be okay. Unless you have a reason to put age squared in there, like a strong reason, say something beyond just the numbers, you might say, well, age squared makes more sense than age because of blank, whatever that is. Then you would probably choose the age squared model. Okay? Look how much lower the age and age squared model is all the way across the board here from the other two. Okay? All right. So let's clean this up a little bit. Now, we're going to, the book says that either one of these are okay, and then everything looks really close for these 3 measures. And so the tipping point, the deciding factor might be that the overall F statistic is higher. I would also say that I just intuitively, I would think that height and age would be better together than height and age squared. It's a lot more difficult to explain the relationship of age squared to y, or weight, than it is just direct age. Why are you using age squared and not using age would be a very big question that people might ask. Okay. So let's look at the 3-model variable, or 3-variable model with height, age, and age squared. And we'll notice that the F statistic significantly smaller or noticeably smaller. I shouldn't say significant. I'm not talking statistically significant. I'm just talking noticeably different. And even though r squared always gets bigger, it's only by 0.0002. So it really did not add much. And we have MSE, but it's getting larger, and we want a smaller one. So that's bad. And then this would be larger, and let's see, p plus 1 here is going to be, p is 3 plus 1, so that's going to be 4. So it's right at p plus 1, but it is larger than the 2.01, and 2.01 is not that far from 3. Okay, so the book says we should consider number 4 or 5, but since the overall F is higher for number 4, we may choose it. I would also say again the argument about the difference between age and age squared, trying to explain that to someone, I would choose age, just practically speaking. Okay, so we looked at, based on r squared alone, the highest for the number one, the best model for one variable would have height in it. And the, supposed to be a G, the best 2 variable model would be height and age, and the best 3 variable model would be height, age, and age squared. Okay, so now about reading the F of P. Model 4, F of age given height is 4.785. For model 7, age of given height and age squared is 0.14. Okay, so it is smaller, and we really want a larger F statistic. That indicates more statistical significance, if you will. And then when we're reading C sub P, I've already gone over this, but you might want to take a look at this and make sure that this makes sense to you. I just did an ad hoc explanation, but here's the formal explanation of the book. All right, now let's talk about backward elimination procedure. Now, the instructor I took this under also says, and I think it's just true in general, that the easier procedures sometimes select wrong models. They're more likely, or they tend to, or are more likely to select poor models or bad models, or even a wrong model, however you want to look at it. Okay. So let's talk about backward selection or backwards elimination. In the backward elimination, we start with a maximum model and we eliminate one variable at a time. A variable, this is one at a time only. Never try to do more than one at a time, okay? So the most common criteria is the partial F statistic. I can say that in my research so far, I think things have changed because I have yet to see anyone use the partial F statistic as the deciding factor. Okay, so many other criteria, but really not the partial F statistic. So I think things are changing in this field. So if we use the partial F statistic, and that's fine, it's going to be using the partial F statistic, we could substitute that for the p-value, and that seems to be one of the most common methods, as you will see, for doing this. Okay, so we calculate the partial F statistics with one less variable, right? So leaving out one variable against the full model. And we evaluate, see, here we go. We evaluate the p-values and compare those with the pre-selected significance level. Now, SAS has a default of 0.1 for the p-value. You might say, well, why isn't it 0.05? Well, this is, you could change this to p equals 0.15. That's a very common value to use for analysis as well. Because what we're doing here is we're not trying to get absolutely significant when it goes into the model. We want to choose the best model. And if it's, and p of 0.1 is still a small probability, right? 0.1 or 10%, that's a small probability. If someone tells you you have a 1 in 10 chance of surviving a procedure, that's a pretty small probability in your eyes, right? So in this case, of course, it's the opposite. So it would be a 90% confident that you'd survive, let's say, if P is greater than or if P is 1.1. Okay. So we're going to compare this, and to put it in the model, or to remove it from the model in backwards elimination, we want the p-value to be larger than 0.1. Another reason for not choosing 0.05 or 0.01 or something like that is that as you remove variables from the model, the variables that are still in the model, their significance can change drastically. Okay? All right. And the third step is if the largest p-value is larger than, in this case, 0.1, then we're going to remove the variable from the model and proceed back to step 1, where we calculate these partial F statistics with one variable missing, right? The variables added last measure, okay, or type 3 sums of squares. Okay, so let's look at this procedure. And so we start off with the, so we've got weight as our dependent variable, and this is step 0. So we've got all 3 variables entered into the model, and we're looking at the overall significance, which the model is significant. Now, so step 0 continued. We have the intercept, height, age, and age squared. Okay. We have the parameter estimates here, the standard error here, and then the type 2 SS. And under this procedure, what this means for SAS is, again, variables added last. All right. I know we've seen type 3 before, but this is a different under the backward selection or elimination, it's called type 2. Now, the partial F statistics, these are the F values, and then the P values that go along with them. All right. So what we're going to do is we usually don't eliminate the intercept, okay, from these variables, from these models. We want to keep the intercept in there unless you have a good reason to remove it. And I would still think about waiting. I would do this analysis with the intercept, and then if I wanted to remove it, I'd do the analysis without the intercept and compare them before I made a decision. Okay, so the one that's circled here on the bottom, this is the smallest F value, which corresponds to the highest P value. That's not always true. Yes, it is in this case, because we're doing the variables added last. So we only have one variable, so the degrees of freedom are going to be the same, okay, in the numerator and denominator. Okay, so it's the largest p-value, so we're going to remove it. The p-value is what we're really looking at. That's what threw me when they said the F statistic, but they're really talking about the p-value that goes with the F statistic, and yes, that is very common. Okay, so the next highest was 0.92 by the and that was for the intercept. But we don't want to make the most common mistake. Some people will look at this and they just go ahead and remove all 3 of these and only leave height. And that's an issue, okay? That is not good. Please don't do that. So here is what we say about the common mistake. You're making the selection based on the maximum model, and I should say, oops, sorry about that, only using the maximum model, so they don't refit anything. So in this case, they wouldn't, again, normally we don't remove the intercept, but instead of just removing age squared, they'd remove age as well. Because age squared has a p-value of this, and age also has a p-value that's much higher than 0.1. However, when we remove age squared, age becomes significant statistically. So never, never, never make variable selection based on the maximum model. In other words, more than one variable at a time. You have to refit the model every time a variable is removed, or else you may be, or probably are, making a mistake. Okay? So I hope that impresses it upon you not to try to shortcut this process, because that is very bad practice. Okay, so in step 0, we look at this, and step 1, we have removed age squared. So age squared is removed. Now, they're giving us the r squared up here at the top. I hadn't noticed that before. It's a little mixed in with everything else. And so the r squared goes down, of course. And here, again, we're highly significant with the model. In fact, we see that the significance has improved. The p-value is smaller than it was with all 3 in there. That also gives us an indication that the fit is better. Now we look at age, and it's the smallest f value and it's the largest p-value, but besides the intercept, but it's not greater than 0.1. It's less than 0.1, so we do not remove it. Okay? So it says that all variables left in the model are significant at the 0.1000 level. And so here is a summary of your backward selection steps. Now, R doesn't do this quite as nicely, but again, R is free and SAS is very expensive, so we'll dig through the data a little bit and make it look nice on our own. Okay, now let's talk about the forward selection. So the backward selection is we start with all the variables in the model, and one at a time we eliminate the worst variable that exceeds our p-value, our maximum p-value, which is the common way to do that. Okay, so now in the forward selection, we start with no variables. So we start with the null model. The null model, just the intercept. Okay, and so we're going to do one variable at a time. This person has said one more variable, but we're adding one variable at a time. So we're doing a partial F test, so just with comparing x2 given x1 after, depending on if there's a variable in there, or the first time we would just be looking at f of x1 versus f of x2 versus f of x3, and we're going to choose the largest f value or the smallest p value, add that variable to the model, and then once we've put that variable in the model, let's say in this case it's x1, then we're going to look at this x2, f of x2 given x1 versus f of x3 given x1. So once x1 is in the model, it stays in the model. And so if we had x1 to x5, then let's say first step, choose x1. So second step, we would look at f of x2 given x1, f of x3 given x1, f of x4 given x1, and f of x5 given x1, and we choose smallest p-value less than our cutoff. In this case, our cutoff is 0.1, but your cutoff could be 0.15 or 0.05 if you really want. But again, that might not be the best method to choose there. Okay, so then let's say that we chose this one, x3, then the next step is going to be, we're going to compare x2 given x1 and x3 are in the model. And then we'll look at f of x4 given x1 and x3, and f of x5 given x1 and x3, and we choose the one with the smallest p-value. As long as the p-value is less than 0.1, then we would add that variable to our model. And we continue until either the p-value is not less than 0.1 for the next variable, for any of the next variables, or you have all the variables put into the model. Okay, so let's go back to our example here. which is simpler. I wish that the book, I know why they chose only 3 variables, but in this case I really wish they had chosen 4 variables, a model with 4 variables to show this procedure so you'd get a better feel of the pattern that's occurring here. Okay? All right. So we looked at this, so in the step 1, so if the small, okay, so we have one or more variables, evaluate the p-values and compare with the pre-selected significance. In this case, it was 0.1, whoops, 0.1. If the smallest p-value is less than the significance level, add that variable to the model and proceed to back to step 1. So, and repeat step 1 might be a better way to say that. Instead of proceed, because it sounds like you're going forward, but then it's saying step 1, okay, which is backwards. All right. So we add this one first, which is the height. And let's see, so here was step 0 where we decide which variable to add first. Once we've added, so step 1, we've added, this was backwards elimination. I apologize. I shouldn't go back to that one. This is the forward selection. So the first step that we're going to do is step 0, everything in the model, or nothing in the model, and we do one at a time, so single variable models, height, age squared, and we choose the one with the smallest p-value that is less than most significant and less than 0.1, our cutoff, and so we add that first to the model, okay? Okay. So step 1 is we enter or add height to the model. Here's our r squared, and then and this is our model, and we look at the model and it's highly significant, and height, of course, is highly significant. It's going to be the same because this is just a single value or single variable in the model to start. Now we're going to look at the conditional F value given, or partial F value, given that x1 is already in the model. So we're going to do that for age and for age squared. And we look at the F values, and this has the largest F value, and this is a smaller P value. And so I said first, but I meant second here. Okay. So we'll add age second because this P value is less than 0.1, and it's smaller than age squared. Okay. Now, okay. So this was step 1. So now step 2 is to add variable age into the model, and we do that, and we see that the model is significant, highly significant, 0.0011, and our F value has increased, or no, actually it has decreased, but that's okay because we're now not comparing one variable only. We're comparing. We've changed the degrees of freedom, but you can see that the p-value went slightly down by 0.0002. Okay, so the model has improved a little bit. Okay, as far as significance, overall significance. Now, so this is our model, and we go to and we look at the type 2 SS and the sums of squares, and we see that here's height and age. Okay, so those are in the model. Now, let's look at, we go to step 3, should we add age squared? So there's only one variable left now. And we look at this, and the F value is really small. Now up here, it was less than, the p-value was less than 0.1. It was 0.06. So if you're just looking at this, you'd think add both of them. But again, that's a mistake because everything's going to change after you add something else into the model. The whole model changes. So once we have x1 and x2 in the model, we look at x3, which is age squared, and the p-value for this, if we add it to the model, is a 0.9, which is bigger than 0.1. It's not only is it not significant, it's greater than 0.1, our cutoff, so we do not add this to the model. Okay, so now we get the summary of the forward selection procedure. Step 1, we added height. Step 2, we added age. We look at the p-value of height and look at the p-value of age in the model with both of them. Okay. They've also given us the C sub p and the partial r squared and the model r squared here. Okay. So that's it for this video. I hope that's helped you understand forward and backwards elimination. Please don't forget to scan your lecture notes by midnight, the date listed in the course calendar. If you have questions, come to virtual office hours. If you can't make it to office hours before you need help, then by all means email me, but please email me a picture of the problem because I may not have it available, and a picture of your work so far so I can see how you're approaching the problem and help you better. Please take care of yourself, and we hope to see you next time.